River is back in the hot seat today. Take it from here.
Thanks, Erica. There is a real-world story behind this topic that ties everything together. Let us start there. Domain 3 of the CISSP is Security Architecture and Engineering, and it opens with the design principles that determine whether a system is secure before a single line of code is written. I am River, your guest host for this episode.
These principles are foundational. They appear in the exam as scenario questions, design trade-off questions, and breach analysis questions. If you learn the principles deeply, the scenarios become straightforward.
Think of these principles as the building codes of cybersecurity. A building inspector does not ask whether a structure looks secure. They check whether it was built according to code. Security architects do the same thing with these principles.
And we will close with the RSA, SecurID breach of 2011, a real case where multiple design principles were violated simultaneously. That breach shows exactly what these principles are designed to prevent.
By the end of this video, Erica and Michael and Bella, you will name every principle, explain the exam difference between fail, secure, and fail, safe, and apply Kerckhoffs' principle to real cryptographic scenarios.
9 concepts, 1 domain foundation. Stick around for the RSA. SecurID breach later in this video. It shows what happens when every principle fails at once. We start with the principle that appears on more CISSP questions than any other least privilege.
Let me introduce the team real quick.
Good to be in the co-host seat for a change. Let us have some fun with this.
Michael here. This is the kind of topic I could talk about for hours.
Bella here. This one surprised me. I think it will surprise you too.
All right, let us jump in.
Least privilege is the most tested design principle in Domain 3. The rule is simple: grant only the minimum access rights a user, process, or system needs to perform its assigned function. Nothing more.
Picture a janitor who needs to clean every floor of a building. Least privilege means giving that janitor a key card that opens cleaning closets and restrooms on each floor, not a master key that opens every room. The janitor's job does not require the boardroom.
Need to know is a related but distinct concept, and it is important to understand the difference for the exam. Least privilege is about access rights to systems. Need to know is about whether an individual should receive specific information, even if they have the clearance level to access it.
A classic example: 2 analysts both hold top secret clearances. One is assigned to a nuclear program, the other to a satellite program. The nuclear analyst has the clearance level, but not the need to know for satellite program details. Clearance is necessary but not sufficient.
Privilege creep is what happens when least privilege is not enforced over time. An employee gets promoted, changes roles, takes on temporary project access, and each transition adds permissions without removing old ones. Over 3 years, that employee has access to every system they ever touched.
The fix, River, is periodic access review, sometimes called recertification. Managers regularly verify that their team members still need the access they have. Anything no longer required gets revoked. Least privilege is not a one-time configuration, it requires ongoing maintenance.
For the exam, remember both principles reduce what is called blast radius, the amount of damage an attacker can cause if they compromise an account. Small blast radius means small breach impact. Least privilege is blast radius control.
Defense in depth is the principle that security should use multiple independent layers of controls so that a failure in one layer does not compromise the entire system. If the firewall fails, the intrusion detection system catches it. If the intrusion detection system misses it, the endpoint detects it.
Think of a medieval castle moat, drawbridge, outer wall, inner wall, keep, and vault. An attacker who breaches the moat still faces the outer wall. Each layer buys time and raises the cost of attack. Defense in depth is that same layered thinking applied to digital systems.
The underlying assumption, and this is key for the exam, is that any single control will eventually fail. Defense in depth does not assume controls are perfect. It assumes they are fallible and designs around that assumption by requiring multiple independent failures to cause a breach.
Zero trust is a more recent design philosophy that extends this thinking to identity and access. The traditional perimeter model trusted anyone inside the corporate network. Zero trust says that network location grants nothing. Every access request is verified inside or outside.
NIST, Special Publication 800 and 207 defines zero trust across 5 pillars: identity, device health, network segment, application, and data. Every access decision considers all 5. The device must be managed, the identity must be verified, the application must be authorized every time.
The critical contrast for exam scenarios, Bella, the old perimeter model, says, if you are on the internal network, you are probably trusted. Zero trust says being on the internal network means absolutely nothing about your trustworthiness. The breach that bypasses the perimeter finds zero trust waiting for it.
Both principles work together. Defense in depth provides layered controls. Zero trust ensures each layer validates independently. Together, they eliminate the single point of trust that attackers exploit.
Separation of duties is the principle that no single person should control all phases of a critical process. It prevents fraud, reduces insider threat risk, and ensures that errors are caught before they cause damage.
The payment example is classic. One employee initiates a wire transfer, a different employee approves it, and the bank executes it. If the same person could initiate and approve, they could transfer funds to themselves. Separation breaks that attack path.
Two-person integrity takes this further. In nuclear weapons protocols, 2 officers must independently authenticate before a launch command executes. One person, even the highest-ranking officer, cannot complete the action alone. The system enforces cooperation.
The exam distinguishes 2 related concepts: dual control and split knowledge. Dual control means 2 people must act simultaneously, like 2 keys turned at the same time. Split knowledge means each person holds part of a secret. Neither can reconstruct the whole alone.
A safe deposit box uses both. The bank holds one key, the customer holds another. Neither can open the box without the other. That is dual control, and it illustrates why split knowledge and dual control often appear together in high security systems.
Privilege separation adds a technical dimension. Different privilege levels handle different functions. A process that reads data should not have write permissions. An account that creates users should not be able to delete audit logs. Separating the privileges limits what any compromise can accomplish.
For the exam, Michael, separation of duties is the administrative control that addresses insider threat. Least privilege is the technical control. Both are required. Relying on only one leaves a gap.
Fail, secure versus failed safe, is one of the most reliably tested concept pairs on the CISSP exam, and many candidates mix them up. The trick is to remember that fail secure preserves security, while fail safe preserves human safety.
Fail secure means when a system fails, it defaults to the secure state, which is denial. A network firewall that crashes and blocks all traffic is fail secure. A door lock that loses power and stays locked is fail secure. Failure closes the door.
Fail safe means when a system fails, it defaults to the safe state for humans, which is open access for emergency egress. A fire door that loses power and swings open is fail safe. Locking people inside a burning building to maintain security would be the wrong call.
The exam trap is that these are not opposites in the moral sense. They serve different protection goals. A data center server room uses fail-secure locks. An emergency exit uses fail-safe. The question is always, what is being protected, data or people?
Secure defaults is a related principle systems should ship in the most secure configuration possible. Features disabled by default, strong default passwords required on first login. Minimal services enabled. The administrator enables what they need rather than disabling what they do not.
The anti-pattern is everywhere in legacy software. Default admin passwords of admin, open ports, permissive ACLs that allow everything until explicitly restricted. These secure default failures account for a huge proportion of successful breaches because default credentials are public knowledge.
For the exam fail, secure denies on failure. Fail, safe allows on failure for life safety. Secure defaults means the box should be locked when it ships, not open.
Economy of mechanism is the principle that security designs should be as simple as possible. Simple does not mean weak. It means that complexity is the enemy of security. Every additional component is another potential failure point and another surface for attack.
A simple encryption algorithm that has been publicly analyzed for 20 years is often more trustworthy than a clever proprietary system that nobody has reviewed. Complexity creates hiding places for bugs and vulnerabilities that simplicity eliminates.
Think of an old Swiss watch mechanism. Bella, every gear has a purpose. Remove a gear and the watch stops. But also, every gear is a point of failure. Economy of mechanism says build the watch with exactly the gears it needs and no more.
Complete mediation means every access request to every object must be validated against the access control policy every single time the request is made. No exceptions. No cached authorizations that might be stale.
The violation pattern: a system checks permissions when a user opens a file session, then caches the authorization for performance. An hour later, the user's permissions are revoked, but the cached session still shows them as authorized. Complete mediation says that cannot happen. Each access must be individually verified.
Performance and complete mediation are in tension. Checking every access adds overhead. Modern systems use reference monitors and capability tokens to balance this. But the principle is clear. Security correctness takes priority over performance optimization.
For the exam, River, economy of mechanism means simpler is safer. Complete mediation means every access is checked, every time, with no permission catching. Both principles reduce the window for exploitation.
In 2011 RSA, SecurID, the company behind the SecurID 2-factor authentication tokens used by millions of organizations, suffered a breach that directly compromised those tokens. This is the design principles case study.
SecurID tokens generate a one-time password every 60 seconds using a seed value unique to each token. The security of the entire system depends on those seed records remaining secret. RSA stored them, and the attackers stole them.
The attack started with a spear phishing email sent to RSA employees. The email contained a malicious Excel attachment exploiting a zero-day vulnerability. One employee opened it. That single click gave attackers a foothold inside RSA's network.
From that foothold, the attackers moved laterally to reach the database containing the seed records for SecurID tokens. Defense in-depth failure. A single phishing success should not have provided access to the organization's most sensitive cryptographic secrets.
Least privilege failure: the compromised account had access to systems it did not need to reach the seed database. Had privileges been tightly scoped, lateral movement would have hit dead ends. Separation of duties failure: the seed records should have required multiple party access to retrieve.
The consequence extended far beyond RSA. Armed with the stolen seed records, attackers could clone any SecurID token EU, and then use those cloned tokens to breach RSA's customers, including defense contractors. The supply chain impact was enormous.
For the exam, remember this one, the RSA. Breach illustrates that security design principles are not theoretical. Each principle that was missing had a specific consequence. Defense in depth would have contained the phishing.
And least privilege would have blocked the lateral movement. Multiple principles working together would have protected the seeds. That is what defense in depth actually means in practice.
Here is what you need locked in for the exam. Least privilege is the minimum viable security posture for any access control decision. Grant only what the job requires, nothing more.
Review access periodically and revoke what is no longer needed. Privilege creep is what happens when you skip that step 2, and it is a major breach enabler.
Defense in depth assumes any single control will fail. Design around that assumption. Zero trust assumes network location grants nothing. Verify everything, every time, from every location.
The fail-secure versus fail-safe distinction is a reliable exam question. Fail-secure denies on failure used for data and system security. Fail-safe allows on failure used where human life could be endangered by a locked door. Know which context requires which behavior.
Economy of mechanisms. Simple security designs are better than complex ones because they have fewer failure points. Complete mediation. Every access request validated every time, no caching, no exceptions. These two principles together eliminate entire categories of attacks.
Kerckhoffs and open design nail down the cryptography questions. The algorithm can be public. The key must be secret. Security through obscurity alone is never acceptable. If you see a question about whether hiding the algorithm is sufficient, it is not.
Drop a comment below. Which design principle do you think is most commonly violated in real-world organizations, and why? We want to hear what you have seen in your own work or studies.
Next up is CISSP 3.2 Security Models, Bell, LaPadula, Biba, Clark Wilson, and the formal frameworks that underpin access control theory. Subscribe and keep the playlist rolling.
Okay, it is quiz time. Let's find out what stuck. Think through each question carefully before you answer.
Hit like if the content is landing, and subscribe to stay locked in.
A server room door loses power and automatically unlocks, allowing anyone to enter. Which security design principle does this door implement? The correct answer is A, failed safe. The door allows access on failure to protect human life and emergency egress.
An organization uses a proprietary encryption algorithm whose design is kept completely secret. According to Kerckhoffs' principle, this approach is considered The correct answer is D. Insufficient. Security should not rely on secrecy of the algorithm. Only the key should be secret.
A user's file access permissions are cached at session start. An administrator revokes those permissions mid-session, but the user continues accessing files for the next 2 hours. Which design principle was violated? The correct answer is C, complete mediation. Every access request must be validated against current policy, with no cached authorizations.
Strong work. Here is what we built today. Security design principles are the architect's checklist, the rules that determine whether a system is secure before it is built. Least privilege, defense in depth, zero trust, separation of duties, fail secure versus fail safe, economy of mechanism, complete mediation, and Kerckhoffs' open design principle.
The RSA, SecurID breach of 2011, showed us what happens when multiple principles are absent simultaneously. One phishing email should not have granted access to the most sensitive cryptographic assets in the company. Defense in depth and least privilege together would have broken that attack chain.
The exam will test these principles through scenarios. A door that opens on power failure is fail-safe. A firewall that blocks all traffic when it crashes is fail-secure. Catching permissions violates complete mediation. A secret algorithm violates Kerckhoffs. Know the principle, recognize the pattern.
Next up is CISSP 3.2 security models. We go into Bell LaPadula, Biba, Clark Wilson, and the formal frameworks that underpin access control theory. Watch that next video now and keep the momentum going.
Subscribe and keep the playlist rolling. Domain 3 builds on itself, and each video sets up the next. Think in pictures, and the answers follow.
Think in pictures, and the answers follow.
Stay curious, everyone.
Impressive work, River. I almost did not want to interrupt. Professor Erica signing off.